Welcome to another science exploration. Today, we're going to explore about how does a battery work. We will see what energy conversion takes place inside a battery. I'm so glad you could join me. Have you ever stopped to think about what's actually happening inside those little cylinders we just toss into our flashlights? We pop them in and bam, things just turn on. It feels like magic, right? But it's not. It is pure science. Let's draw back the curtain and see what's really going on in there. So let's kick things off with a simple definition. A battery is basically a device that changes chemical energy right into electrical energy. And it does this using chemical reactions happening entirely inside it. Just think about that for a second. We are literally taking chemicals, mixing them up in a very specific way, and creating usable electricity. It's kind of like having a tiny portable power plant sitting right in the palm of your hand. All that chemical energy is just locked up safe inside, waiting for the perfect moment to be transformed.
All right, let's look at the actual anatomy of our little power plant. There are three absolute must-know parts here. First up, we've got the positive terminal, which we call the cathode. You'll almost always see a little plus sign right next to it. Then, on the complete opposite end is the negative terminal, the anode, marked with a minus sign. But here's the real secret sauce, the electrolyte. This is a chemical liquid or sometimes a paste crammed right between those positive and negative terminals. It is where all the exciting chemistry happens. Think of the cathode and anode as two separate rooms, and the electrolyte is the hallway connecting them.
So, what exactly goes down when we put these pieces together? Well, chemical reactions begin. The chemicals naturally start to interact, and as they do, they build up these tiny, microscopic particles called electrons. Now, you can't see electrons with your naked eye, obviously, but they are the absolute superstars of the electrical world. As that electrolyte chemistry keeps bubbling away, more and more of these little electrons are born. They're the tiny engines driving everything we're about to see.
Now, because of all those chemical reactions, we get a massive traffic jam. Extra electrons start piling up right at the negative terminal, the anode. Imagine a huge crowd of people all shoved into one tiny little room. It's packed. But at the exact same time, the positive side, the cathode, it's left with hardly any electrons at all. It's practically a ghost town over there. So we've got this huge imbalance, a super crowded negative side and a totally empty positive side. Well, nature absolutely hates this kind of imbalance. So these electrons, they want to move. They're pushing, they're shoving, trying their hardest to get away from that cramped negative terminal and head over to the roomy positive terminal. But here's the kicker. Remember that electrolyte paste in the middle? They can't easily pass through it. It's like a giant locked door. So they're stuck. They desperately want to reach the positive side, but they're completely trapped on the negative side. So how do we help them out? We build them a bridge. The second we connect a metal wire from that negative terminal all the way over to the positive terminal, we give those trapped electrons an easy escape route. And man, do they take it. The moment that wire is connected, the electrons go rushing out of the crowded negative side, zooming through the wire, and happily arrive at the empty positive side. And guess what? This moving flow of electrons, that is exactly what we call electric current. Boom, we've made electricity. Now hold on just a second. I want to pose a quick question. Why do we call this specific flow DC current? You've definitely heard that term, right? DC. Maybe you've seen it stamped on a battery or printed on a toy. But what does it actually stand for and why does it matter? Let's take a closer look at the actual journey those little electrons are taking. Here's the secret. The reason we call it DC is all about direction. Once those electrons leave that negative terminal, they only have one single path. They travel from negative, right through the wire, straight to the positive terminal. They always flow in the exact same direction. There's no turning around, no U-turns, no going backwards. It is a strict one-way street for these guys. And because that flow is so incredibly steady, since the direction never keeps changing back and forth, we say the battery produces direct current, or DC for short. It's direct, point A straight to point B. This is actually completely different from the electricity coming out of your wall outlets at home, which flips directions constantly. But for batteries, it's always a smooth, continuous, direct current. So what does this all mean for us? Well, this direct current is exactly what powers our everyday devices. That flowing electrical energy is the magic ingredient we need. We literally just place our device, like a little light bulb or a tiny motor, right in the middle of that wire path. And as those electrons rush through the device to get to the positive side, they do the hard work for us. Just look at how this plays out in real life. We take that DC electrical energy and we transform it into other types of energy we actually want. Like if you put a flashlight bulb in that wire path, the electrical energy suddenly turns into bright light energy. If you hook it up to a little portable fan, the battery's energy turns into mechanical energy, spinning those blades. Attach a speaker and you get sound energy playing your favorite songs, or put it in a toy car and that electricity turns right into movement. Let's quickly recap the whole shebang, step by step. Step 1. Chemical energy. The chemicals inside our batteries start reacting. That immediately leads to step 2, the movement of electrons. The reaction creates a huge pileup of electrons on the negative side, and they come rushing through our wire bridge to get to the positive side. Which brings us to step 3, DC electrical energy. That continuous, one-way flow of electrons gives us the usable direct current we need. And there you have it. A simple battery converts chemical energy into DC electricity just by pushing electrons in one direction. It is honestly amazing to think that every single time you switch on a flashlight, you're unleashing this tiny, invisible chemical reaction that sends millions of particles zooming down a wire. It definitely makes you wonder what other invisible forces are powering the world around us. If you found the video informative, please like the video. Thanks.